My landlord wants to meet and discuss why my heating bill is so high. I told her, my door is always open. Yes. That has to do with thermal energy transfer. So we're going to talk first about the different methods. And there's going to be three main things that we're going to discuss here in this video. So it's going to be these different ways in which thermal energy or heat is transferred. And don't forget what heat actually is. Remember, that's Q. Q is heat, right? That's Q equals heat. And remember, that's measured in joules. Don't forget that. So we're going to be transferring heat in three different ways, or at least thermal energy, so through conduction, convection, and radiation. So we'll start with conduction. Okay, so we have thermal conduction, and that's when we transfer the energy without any bulk movement of the particles. This is the key right here, okay? It's the fact that we don't have any particles actually moving from one place to another. It's actually through this other process here I'm going to describe. Whereas you're going to see convection is when you do move all the particles, you have a bulk movement, and there's an overall movement. Here, though, particles aren't necessarily like flowing. It's not like a river or anything. It's that things are close to each other. And you're going to see that's because it's a difference in kinetic energy. In other words, the temperature of the particles. And don't forget about temperature. Remember, temperature is the average kinetic energy. And what does that mean? Well, that means that things that are hotter go faster. So let's consider an example like a frying pan, for example. Where here we have heat right here. So this here, heat. And then we've got this cooler handle, for example. Okay, so we're going to have that the vibrating molecules here are going to transfer kinetic energy to these free electrons that are hanging out. So then we're going to have that the electrons then are going to transfer energy to the colder or slower parts. Well, that means it's going to increase the kinetic energy, so that means it increases the temperature, like we're just talking about here, and that's why the handle actually gets warmer. So again, it's kinetic energy that's in a sense being sort of transferred over there. So if we think about the direction of Q, in other words, the direction of heat transfer, it's going to go like this from hotter to the cooler, and that's going to sort of slowly, that's why if you have a pan that's got a metal handle on it, for example, it's eventually going to get hot. Like metal particles didn't have to transfer over there. It's that the fact that they're near each other, you know, some of them shake and those make the next ones hotter, those ones shake, those ones make the next one hotter, and so on and so on. So it sort of flows this way. Same thing with like if I'm holding a snowball, for example, my hand is hotter, for example, and this snowball is cooler. Of course, what's going to happen is, you know, thermal energy is going to go up this way here. So that's going to be Q is going to go up and sort of melt the snowball. Okay, so still related to thermal conduction is something called thermal conductivity. It's this property of materials. So if you imagine this sort of cube or this block right here with this area A right here like this, and we've got heat coming in, you know, this heat transferred, for example, or energy transferred. We've got initial temperature maybe here, and then we've got a final temperature here, T2, and this is the thickness of this block. So if we have it like this, so delta Q, for example, is the energy transferred. We're going to have a delta T, which is a time. A is a cross-sectional area. That means it's going to be this. Delta T is going to be a temperature difference, which is going to be T1 minus T2, and that's probably going to be in, let's do it in Kelvin, for example. We're going to have a thickness of the material in meters, and we're going to have this property called thermal conductivity. But first, let me write down the equation that governs this behavior. Okay, so this equation here goes delta Q, delta T equals K times A times delta capital T over delta X. This is an equation you have on your data booklet, so you don't have to memorize it, which is good, and we'll discuss it. So what's going on right here? Well, if we first of all, if we look at this one here, delta Q over delta T, what does that mean? That's like joules per second. This is a power. That's like in watts, for example. So I'm just looking at the units right here. This would be in watts. Okay, and then we've got this K, okay, fine, times area. Area has units of meters squared. And this right here, delta T, has units of Kelvin, and delta X has units of meters. So if I'm trying to get the units for K, just to figure out what K would be, will be, and let's see, it would be in watts, for example, yes. And then this meters squared per meter, do you notice, and these right here will cancel out, and you'll just get a meter here. So it'll be watt, and then the meter will come on the bottom, so that means I'll say over meter and Kelvin. So that means the units at least will be watts per meter per Kelvin. That's why the units right here then for thermal conductivity are watts per meter per Kelvin. So this is just an analysis of the units, for example. So just to take a look at that. But this basically defines, this thermal conductivity, it's a property of different materials. Okay, so for example, if it's got a higher K value, it means it's easier to transfer energy. So, it's something that it doesn't take a lot to make it warm up or heat up. So that means, for example, like iron or copper or something like that, some metal, those tend to be things with higher thermal conductivity. Now, by contrast, something with a lower K, a lower thermal conductivity, that means it's more difficult to transfer energy. It doesn't conduct thermal energy very easily. So it's something like an insulator. That could be like cork or air or something like that, something else that it really insulates. Now, before we talked about thermal conduction, where there wasn't a bulk movement of particles, but now we're going to have a bulk movement of particles. That's called thermal convection. So thermal convection is very, very important. That's why I put this little joker here at the bottom with Kermit. But there we go, Kermit the Frog. But basically, it's due to variations in density. This happens in liquids and gases. And let me just give you an example. So this, for example, at our house, for example, in Denmark, we have a little house there, and we have a heat pump. So it's actually set at the bottom, even though the guide says it's supposed to be at the top. But my wife doesn't like it at the top. We put it at the bottom. There we go. We've got a heat pump. What it does, it just spits out hot air. Now, what happens with that? Well, hot air, it has a lower density. And things that have a lower density will then naturally rise. Well, that means it's going to pull in the cooler air then behind it. So it's going to, as the hot air goes up, the cooler air then is going to be pulled down. Now, what does that do? That creates what we call a convection current. So again, as hot air with a lower density goes up, it rises, that's going to pull down then some of the cooler air. So the cooler air goes down, the hot air goes up, and of course then what's going to happen is going to keep going like this. We're going to have this convection current. Now, what does that mean for us? We actually feel a breeze. Like we'll actually feel a breeze in the room right here. Not just from the hot air, but it's because the hot air is creating this whole cycle here. Maybe I'll draw it actually. So I'll draw it like this here. So the hot air right here, this is the hot air goes up. And what happens, of course, then it pulls, at the same time it pulls down this cooler air like this. Cooler air. And what happens then is you end up, feeling this you kind of feel this breeze. Now, that can happen in air, but it can also happen in liquids as well. So there we go. So that's thermal convection. Now, last but not least is the third and final method of thermal energy transfer, at least that we're going to be discussing here, and that is going to be radiation. So that's a transfer of energy because of electromagnetic radiation, which is just a fancy way of saying light. So interestingly about light, it doesn't need a material through which to travel. So for example, conduction and convection, it actually needs something. For example, with conduction, you need a material in which to, transfer the kinetic energy to go back and forth to vibrate the next particle, the next one, to make it hotter. With convection, you need actual bulk material to, be going over either, a liquid or a gas or something. But light doesn't need that. It works perfectly fine in a vacuum in outer space. That's good because otherwise we wouldn't be able to see the sun. So we're going to go much deeper on this with black body radiation, for example. There we're going to see these equations like the luminosity, for example, of a star is sigma AT to the fourth. We're also going to have one for the apparent brightness of a star, which is the luminosity divided by 4 pi times the distance squared. But basically, light, it has different properties depending on its wavelength. That's the key thing. So different colors of light do different things. Some light we can't see at all, some we can, right? That's the visible light. Some light is redder than red, we can't see it, we call it infrared. Some light is, purpler than purple, we call it ultraviolet, for example. And one example of an interesting, type of light or color of light is microwaves. So microwave, for example, has a wavelength of, around, it could be like 30 centimeters all the way up to about a millimeter. So something like that, for example. And microwaves, a very special property of that one is that water molecules can be excited by that. It's close to their resonance frequency. So basically what happens is if you take, for example, water in a cup and you put that in a microwave oven, what that does, it just shines that color of light on them. But what does that do? It just happens to be that color of light happens to make those water molecules vibrate. And when water molecules vibrate, they get hot. So that's why that kinetic energy goes to heat. That's why we use microwaves for heating things, for example. Now, not all colors of light do that. Different colors of light do other things, like X-rays, for example, are useful because they go through our soft tissue, but they don't go through bones. So we use that, to take pictures of bones. All sorts of examples of different light. But just so you know, at least thermal radiation is just when that's when light is used to transfer energy.